Good, shall we begin? In today's episode, we'll be solving a problem from a class that I failed. It was the first year, second semester in algebra, and I didn't do quite well there, but we'll try to solve all the problems I didn't do, and maybe next year I get a better chance. And you see the problem on the screen. Let's try to solve it. So to have the Galois group, we need to talk a little bit about the element that we use to generate a new field. Okay, I don't really want to write it each time, so we call it alpha. So square root of 2 plus square root of 3. And firstly, we want to find the irreducible polynomial of alpha that we'll call p. So let p of x equals to irreducible polynomial over q, the field that we have here of our element. Great. And the next part, so to calculate it, we need to have a polynomial with coefficients in rational numbers. So maybe we take alpha square. So if you square it, you get 2 plus 2 roots of 6 plus 3, or 5 plus 2 roots of 6. Good. So we have something, but we still have a square root here. To eliminate it, we probably say that alpha squared minus 5 over 2 squared is actually 6. And if open parentheses, we get alpha to the power 4 minus 10 alpha square minus 25. So here we multiply 6 and 4 equals to 24. And oops, we got to have 5 plus here. And finally, what we do, we say plus 1. So easy. Now we need to check if it's irreducible or not. It's usually what you do in middle school. And to solve it, what we do firstly, so it can be split all in a product of polynomial degrees 1 and 3, or 2 and 2. So 1 and 3, the way we check it, we say that if it's split in 1 and 3, then it has a root, rational root. The possible roots in rational numbers are only plus or minus 1. Roots from Q are possible. Roots are potential roots are plus minus 1, but you see easily check that they do not satisfy because we have 10 here. So 2 and 2. So there is no easy tricks here. So we suppose that it is splitted. Oops, we need to have power 2. So let's introduce 4 new variables. We have product here, and that means that where those variables are q, then what we have, if we open parentheses, we get the left hand side gives us f squared plus a plus c. Oops, we should have power 4, here power 3, plus when you have 2, it's actually b plus d plus a times c plus times square. So the first power is AD plus BC far, and then BD. What you have a system of equation on coefficients. So you have A plus C is 0 because we have now alpha power to 3 here. This one is 10, minus 10. This one is AD plus BC. Is 0. And B times D is 1. Great. So I propose to call did we get everything right? Yeah, probably. So propose to call B is equals to D times the inverse of D, and to call C is minus A, and we plug it back, we get 2 more. So plug it in the first one, we get D, the inverse of D plus D plus actually minus A square. Is minus 10, and we get A times D, B is D minus 1, and C is minus A, so we parked in the minus, we have A, good, so it's 0. So actually from here we get, for example, it would be a case where A is 0. If A is 0 here, then it's 0 also here, and we get D minus 1 plus D equals minus 10, or if we multiply everything by D, we get 1 plus D square equals to minus 10D. So potential roots are plus or minus 1, and it doesn't work. Good. The other case is D minus 1 is equal to 0, or D is equals to plus or minus 1. Then we get then we get plus or minus 2 from here. minus a square equals minus 10. So we say that a square is equals 12 or 8, and a is not a rational number. So nothing here, and we say that this thing is irreducible, and actually we found the irreducible polynomial of alpha. So p of x is equals to x4 minus 10x plus 1. Oops. Okay, good. It seems to be correct. Okay, so we found a reducible polynomial, and now we need to check that the extension is a Galois extension. To do so, actually, as we are over rational numbers, we only need to check normality of extension, and that means that actually we want to prove that all roots of this polynomial is in our field. And to do so, we need to solve it. It's also what you do in middle school, because you need to just 2 times you need to solve a quadratic equation. The way you do, you take d over 4, and d over 4 is 25, 5 square minus this times this, so minus 1 is 24, or it's 4 times 6, or it's 2 times root of 3 square, root of 6 square. Good, and then we say that actually alpha square is equals to 5 plus or minus 2 square root of 6. This gives us actually it's what we have just seen, plus 3, and this is actually what? Square root of 2 plus or minus square root of 3 square, and thus we say that alpha is equals to plus or minus square root of 2 plus or minus square root of 3. Good, we have found all solutions. Great. And the next things to check, if we have all those solutions in our field, then we have square root of 2 square root of 3 inside, and vice versa, we need to check. So what we know actually from here, we know that this part is in Q with alpha. This means that we get square root of 6 inside. So it is inside. And thus we can look at the following expression. Square root of 2 plus square root of 3 is also inside. Here we get 2 square root of 3 plus 3 square roots of 2. Inside we have also just the sum of 2 roots inside because it's alpha. So inside we have square root of 3 plus square root of 2. So we take those two together, and you can easily check that actually if you subtract this one from these 2 times, we get square root of 2 inside, and actually square root of 3 also inside. Great. Thus extension is Galois. Thus we have extension. So it's very simple. Usually you see in second semester your algebra program, university. You should see this. And now the question is about what is Galois group of this extension. And to check it, we need to do so we call G this group, perm G of this extension. Okay, we got it. So actually this is the set of morphisms of fields, actually of Q alpha to Q over Q. This means that it fixes the rational numbers, each rational number, and what we know from a general theory from your class, you know that if we have something inside, then if you apply f to alpha, is also root of P. Great. So and then we have alpha roots, and so it's a permutation of roots, and we need to take a subgroup of permutation, but each f, oh Jesus, each f is determined by image of our alpha. Why? Because its image can be only in actually the way to write it probably is to write as G times alpha is actually the following set is a set of roots where wrong parentheses, where those roots we've seen them earlier, so this is those roots, and by the property, by inverse property of polynomials, because actually we derive our extension from polynomials, the f is determined by the image of alpha. Great. So that means that then we have exactly 4 elements in G. That's 4. This gives the following fact that G is Z over 4Z, or it can be actually the Klein's group, K4, and now we need to choose one. So how do we choose one? Oh, actually, I know how we choose one. So one of the basic facts from Galois theory that if you have a finite extension, then each subgroup corresponds to a subfield that it is between the ground field and the field we are discussing. And what we have actually between q root of 2, q root of 3, we have in between. on this outfield, and that means that we have at least 2 subgroups. There can be more, but we have at least 2. And from your first semester, what you should retain is that in cyclic groups, in Z over 4Z, we have only 1 proper non-trivial subgroup. Yep. And in K4, we have 2 of them. We really have 2. Yes, we have 2. And then with this, with keeping this in mind, the G is actually K4. Great, we found the group. I think that was the second part of the question. So we need to describe all intermediate subfields. Okay, it's easy because of the idea that K4 has only 2 proper non-trivial subfields, subgroups. Thus, we have only 2 intermediate fields. Okay, it's done, and they are Q2 and Q3. So if you want to learn more about this topic, I encourage you to read the Serge Lang's book. It's very good. It's very accessible. You can try and read. So about groups, you need to read maybe first 30 pages, and then you can read the section about fields. It will be 40 pages more, and you can solve problems like this. See you next time.